Yeah, so today I'm going to defend my thesis. I've got a story to tell. I imagine you guys are here to hear a story, right? I'll make the abridged version here for you. Let's see if I can figure out this. I'll start off with a overview map, so it gives you from a larger perspective of where I was working. I'll introduce you to the hydroclimate of the Mojave Desert region, specifically the El Nino Southern Oscillation, ENSO, if you've some of you've probably heard the term, and the Pacific Decadal Oscillation, the PDO. I'll also give you some information on the Mojave Desert region climate conditions. I'll give a little bit of a background on the study site, some of the human impact at that study site, the modern climate, and the paleoclimate. I'll run through the methods and the results, and then I'll discuss those results in terms of climate interpretation, 12,000 year history of hydrologic variability, and climate forcings, and then I'll give you the conclusions. So we'll start off big. We've got the North American continent, and then we have the Mojave Desert region here in the green. I thought that was pretty impressive. It covers 152,000 square kilometers. We'll move in a little bit closer here. So now you can see the state outlines here. We've got California, Nevada, Utah, and Arizona. The Mojave Desert region again in the green. We have the black outline is the Mojave National Preserve, and Ford Lake is our red star, the approximate location. Keeping an eye on the longitude, the West 117, that becomes the demarcation for our precipitation cycles. To the west of the 117, we generally get a winter-dominated, or called the coastal conditions, and then we have a bi-seasonal to the east of the 117, where you get a winter and a summer precipitation. And Ford Lake, as you can see, is bi-seasonal. It's east of the 117. So basically, climate conditions of a location, region, or a country impact productivity and profitability of that area. Within the Mojave Desert region, it is characteristically dry, and then we get interludes of precipitation, where the average annual rainfall is 137 millimeters. And to give you an idea of what that's like, here at Cal State Fullerton, we get 356 millimeters a year. So as the population increases in Southern California, and we're pushing into an area that receives very little rainfall, it's making it vital that we understand the paleohydrological pH changes in climatic forcings of the Mojave Desert. So a Google Earth map of the Mojave Desert region. We've got green outline this time, not filled in, following around here for the Mojave Desert region. We've got our Mojave National Preserve in black again, our Ford Lake as the red star. And then we have a Mojave River line here that I'll explain here in a little bit. The purple dots, the purple push pins are our cities, and I'll label those in a second just to give you a heads up. Our light blue push pins are our coastal comparison sites, so basically winter-dominated coastal sites. And again, just to remind you, we've got to the west of the 117, we end up with our winter-dominated, and then to the east, we have our bi-seasonal, where we have summer and winter. There's our Ford Lake. So, and to the north, we have Las Vegas up here. And to the west, we have Barstow, Searchlight, Nevada, and Goffs, which is the little town just that you turn off to go into the Ford Lake location. Our comparison sites will start up here. We've got Abbott Lake, Zaca Lake, Lower Bear Lake, Lake Elsinore. Oh. And then we'll move in here. We've got some lakes that are the Mojave River fed lakes. So we have Soda Lake, Silver Lake, and the East and West Cronies Lakes. I also have in the white push pins, we have Indian reservations that will come in, I'll be talking about here in a second. We have the Fort Mojave Reservation, the Chemehueve Reservation, and the Colorado River Reservation. Ooh. So basically the modern hydroclimate of the Mojave Desert region is influenced by Pacific Ocean atmospheric phenomena, specifically the El Nino Southern Oscillation, the ENSO again, and the Pacific Decadal Oscillation. For the El Nino Southern Oscillation, it's defined as the quasi-periodic climate pattern. It has a 2 to 7 year shift, and it typically lasts 9 to 12 months. This is occurring across the tropical Pacific Ocean. And when we get warm sea surface temperatures, which you can see right here in the red, the darker reds are warmer sea surface temperatures in the tropical Pacific Ocean, we end up with ideal El Nino conditions. And this is generally when we get wetter winters in California. We have the ENSO, and so ENSO and winter precipitation in the southwest United States fluctuate depending on the phase of the Pacific Decadal Oscillation, the PDO. The Southern Oscillation Index is frequently used as an index of ENSO, and I'll be interchanging SOI with so you know that it's the El Nino conditions, and these conditions are reversed for the La Nina. For Pacific Decadal Oscillation, it is a pattern of Pacific climate variability, similar to ENSO in character, but varies over a much longer time scale. So typically we get 20 to 30 years for the PDO. And to give you a visualization here, I've got Ford Lake and the White Star this time, so you can focus on this region of where we are. And when I talk about whether they're in phase, so it depends on whether the PDO and SOI are in phase. We want warm sea surface temperatures for El Nino. We want cool sea surface temperatures for La Nina. When they're in phase we'll have either a positive and a negative, or vice versa, and we'll get amplified signals. So basically, when we have a negative SOI and a positive PDO, down here where Ford Lake is, we're going to have a strong precipitation signal coming in for the El Nino. And that's what was predicted for the our Godzilla El Nino, I think, is what we were predicting this last El Nino episode. And then when we get the in-phase PDO and SOI for the La Nina conditions, then we end up with extremely dry, which is probably what we'll end up this winter, possibly. When they're out of phase, then we have the same symbols together, so we have positive, positive, negative, negative. And then we end up with this diminished precipitation signal down here at the bottom. And when it's in the La Nina phase, then we end up with a diminished drought condition, the drier conditions here. All right, so why Ford Lake? We got Ford Lake over here in the red star. We have our Mojave National Preserve in the black again. We have the Mojave River here, and just a little bit of the outline of the Mojave Desert region and some of our comparison lakes. So today, there's no temporally continuous paleolimnological research sites with a Mojave-only climate signal. The majority of the lakes studied, and that would be in this area, are Mojave river-fed lakes. So we're basically getting a coastal signal, that because the precipitation drops here and shoots down to these guys. So the headwaters up in the San Bernardinos there. Here's a topographic map of Ford Lake. With the greenish color is our watershed, and it's relatively small, and we're contained within the Mojave Desert. So we chose it to reveal a Mojave-only pH record. And here we are again, a little bit closer up here. We got our Ford Lake and the red star. We have our soda, silver, and our cronies over here in the Mojave River. Our objectives were to reconstruct the hydrological variability of Ford Lake over the past 1,200 years. We want to compare the Ford Lake data to winter-dominated coastal climate records, and to identify and explain the climate-forcing mechanisms driving Ford Lake pH. We believe the hydrologic variability at Ford Lake will be characterized by a shift marking the medieval climate anomaly, the MCA, and the Little Ice Age boundary from a generally drier during the MCA to a wetter LIA. The dominant forcings driving hydrological variability at Ford Lake are ENSO and the PDO. So a little bit background on Ford Lake. It's an ephemeral lake, which means that it's typically dry, but it fills up when it rains. Or not fills up, but it'll start to fill when it rains, depending on how heavy the rains are. The maximum historical lake depth, we estimated at approximately 8 meters for the lake. We have a Watson Wash berm, and it's just like a hillside in a sense. When you're out there, it doesn't look like much, but we use that elevation down here, which is the lowest, at 1237, which would be the spillover point if it was to, if ever spill over. And this gives us the drainage basin parameter again here. We've got roughly 33.5 kilometers. So Ford Lake again there. We have the watershed, just to give you another perspective of the area. And we have a Mojave Road, which I'll explain here in a bit. So a little bit about the human impact to our site, which is kind of a cool little story. I'll do a real brief background on the Chemehueve and the Mojave tribe. So pre-European contact, approximately 2,000 years ago, the Chemehueve and the Mojave tribes wandered the Mojave Desert region. They were hunter-gatherers. Our first documented European contact was 1775, where Francisco Garces was the first European to make contact with Mojave. He kept really good records. He was also the first non-native to journey across the desert to the coastal area. And part of a leg of his journey ended up being called the Mojave Road, which I showed you in the slide before. Around 1810, both of the tribes eluded a Spanish slave raid and a smallpox epidemic by moving out of the desert into the southeast area by the Colorado River. 1865, there was a 2-year war incited between the Chemehueve and the Mojave, so they didn't always get along. By 1907, we established the Chemehueve Valley Reservation, and shortly after, we ended up with the Fort Mojave Reservation. And in 1940, the Parker Dam flooded the Chemehueve Valley area, forcing the tribe to move down to the Colorado River Reservation. This gives you an idea here. I marked where the Colorado River is, so you can see where we are spatially on the map. We've got Ford Lake again as in the red star. The purple square is Las Vegas. During the claims case, which is basically they used oral traditions and historical information and compiled it to create the federal Indian lands claim. So the Chemehueve had the blue area here, and the Mojave had this little section along the river. And there's our Mojave Road again. Here's a map of Ford Lake in the how it's approximately 5 miles from the Mojave Road. So David Nichols did his thesis. He's an archaeologist. He did his thesis, and part of it was at Ford Lake and the Hackberry Mountains, which is the mountain range right behind here. And the pink dots here are basically his site locations where he found artifacts and whatever the archaeological pieces that he was looking for. He ended up finding the stone mono and metate fragments, which is in the picture there. Lithic scatter, sleeping circles, house rings, fire rings, diagnostic biface, which is basically when they're making their stone tools or the stone weapons, when they start chipping away but they didn't finish the project. The pieces that get chipped away are the actual product that just didn't work out for them when they're napping away at the stone. They find those there, and up in the Hackberry Mountain area. Now, he didn't date his artifacts, though I found that the stone monometates began to appear in Southern California during the milling stone culture, which is basically 7,500 years ago. So that's kind of cool. So the close proximity to the Mojave Road and numerous artifacts found in the region all add to the likelihood that the Mojave, the Chemehuevi, and other tribes utilized Ford Lake. We'll move up to the homesteaders. So in 1909, there was an enlarged Homestead Act, which is basically just increasing the land size that they're going to give the homesteaders. To stake a claim, a settler just had to live on the land for 3 years, plant crops. I found that they didn't have to be successful. I think desert farming. And file proof of cultivation. Once the terms were fulfilled, the patent would be issued, giving them full title to the 300 acres to the claimant. And Harry Truman Ford was an Eastern Mojave homesteader and the namesake for our Ford Lake, and his family still has the land there. We got some pictures here I'm going to show you from a great-great-grandson, which is kind of fun. Here's the land, a picture of a photocopy of his land deed. That's a photocopy of a photo of his Ford family homestead, which I think is kind of cool to see the old pictures. The Ford family there. Now, we're wondering why I'm bringing up people or humans, and basically we're trying to figure out in a small little area of the Mojave Desert what kind of impact the humans might have had, and does it show up in our cores, and we'll find out. We'll move on to the modern climate in the Mojave Desert region here. So we have the precipitation in that region is primarily driven, we know, because it's the biseasonal, by winter and the monsoonal weather. We end up during the early summer, we have less than 5% rainfall. Late summer, early fall, that's during our monsoonal time, we end up with only 29%. And then 66% comes during the winter. So winter is still dominating our precipitation cycle out at the Ford Lake area, in Mojave Desert region. We have in our core covered 12,000 years, and it has two specific time phases, for lack of a better word. We have the medieval climate anomaly here, which is the bottom of our core. It is characterized by cool central and eastern Pacific sea surface temperatures. This created intense centennial scale droughts. Multiple paleoclimate proxy data suggests the northern hemisphere circulation patterns are approximately equal to our La Nina conditions. So in a nutshell, the MCA is characterized as drought-like conditions. We use tree ring chronology to recreate the PDO that I talked about earlier. We have pack rat middens. Here's the pack rat. Here's his middens. If you weren't familiar with the pack rat. We use comparison lakes, which I've shown you in our little blue push pins, which are winter dominant, our coastal signal. There's those. We'll move up to the Little Ice Age, where multi-proxy climate records from the Western and Central North America reveal the transition from the MCA to the LAA as a shift towards increased precipitation and decreased summer temperatures. So we move from the MCA drought-like conditions into a wetter and cooler climate. The tropical Pacific sea surface temperatures transitioned from cool warm waters, which is the La Nina, to warmer El Nino conditions. And we used, again, tree ring chronology, pack rat middens from the Mojave Desert region, and comparison lake data. So the importance of this Ford Lake data is that it will be the first Mojave Desert region lake site with a Mojave-only climate record. The comparison site data are winter-dominated signals. So now we can see how similar or different the Mojave-only climate is from the coastal. We're going to compare the data from Ford Lake to the coastal and then see what's similar and different between them. The resolution of Ford Lake data should allow us to determine how Ford Lake responded to its coastal counterparts. And we can infer then the role that coastal climate winter basically plays in the Mojave Desert region during the late Holocene. We'll do for methods, we had sediment collection, age control, magnetic susceptibility, loss on ignition, We did microfossils and grain size. Here we are digging. This is actually a push core in a trench. We took out 6 sediment cores. One of them was a trench. We ended up losing the equipment and running down a trench, hand digging a trench, and then figuring out how to push core again. So here's Kirby's turn in the ditch, digging out, and Kirby's in the trench, sampling each centimeter down. We've got our measuring stick here. We're measuring and putting it in a baggie labeled for each centimeter. I'm in the lab here pushing the cores that we got up and bagging them. For age control, we use 7 discrete organic pieces. We use seeds, roots, charcoal, all sampled at various depths. They were measured using the accelerator mass spectrometer, carbon-14 dating. For magnetic susceptibility, we use the Bardington MS2. Loss on ignition, we did a percent total organic matter, the percent TOM, and the total carbonate percentage. That's the 550 and the 950 burn in this cool hot oven. Using the Dean loss on ignition method. For grain size analysis, we conducted, after chemically preparing the sediment, we used the Malvern. And our results, I'll talk about the sediment description, age control, magnetic susceptibility, loss on ignition, microfossils, and grain size again. So for sediment description, I threw all of the sediment data that we got from the Malvern, threw it into a ternary diagram, and we ended up with primarily massive brown clayey silt. We were unable to do a stratigraphic profile because the cores were extruded vertically or in situ. And could not be carefully described. Our age control only returned 1 good date, so we have a really nice age model. It was found at the 173, 175. The other 6 materials were either too small for radiocarbon measurements, or they contained excess C14. Likely from the 1950s thermonuclear weapons testing. So everything was modern, other than the one charcoal bit we found at 173. Now here's all the Ford Lake data raw. Not raw, but without any markings on it, so you could see, and you start to see patterns, right? Nothing, just squiggles, right? So what I'm going to do here is I'm going to put up where the IPCC, which is the Intergovernmental Panel on Climate Change, they've all agreed upon a certain time range for the MCA and the LAA. And I'll give that so you can kind of get an idea of what areas we're looking at here. For the magnetic susceptibility, it's a very small value. We've got it goes up to 9 here. And it's basically the trend line is invariant. It's pretty much straight lining across. We have a few blips, but nothing that's exciting. Our percent total organic matter is pretty much doing the same thing. Low values as the magnetic susceptibility. Excuse me. Our percent total carbonate is pretty much non-existent. Anything below the 4 is a clay dewatering issue. And the little blips coming up here aren't telling us anything significant at this point. The grain size percentages, like our little birthday present in our package, we've got our percent clay, silt, and sand, and they're the ones that are showing the most variability. So we've got, within the MCA, we've got some peaks going on, then we kind of flatline, and we're looking at trends, not every single peak. So we've got the sand here, which becomes an important player here, and it's pretty much flatlining right around here in a trend form. And then here, up in the LAA, it starts to peak, fluctuate. We got a lot more fluctuations, and it's also increasing to the present time. Charcoal is basically flatlined from the bottom of the core all the way up until we hit about the end of the LAA, and then it increases exponentially towards the present. The Bruvbina is pretty much doing the same, except for I believe it goes back maybe about 300 years instead of 100 like the charcoal. and our percent grains greater than 2 millimeters, and our average grain sizes are fluctuating quite a bit. We've got a lot of action going on down here throughout the core, and as well as at this point here, we've got more going on, and then it starts to decrease slightly. All right, so now I'm going to discuss the results. Age control, I'll start a climate interpretation based on sediment. We have a grain size, microfossils, 12,000 years of hydrologic variability at Ford Lake and Ford Lake climate forcings. There's our wonderful age model. Perfect. We have this is the 173 centimeters down with our good 944 calendar years BP. We also have the point where we took the cores, the surface water interface. 2015 is when we went out there for this project. The ones in red are falling in line here. Those are the modern ones that we tossed. They didn't, they weren't reliable. What I end up doing here, the squares, we have the first charcoal spike. If you take the depth and the age here, and it starts to fit pretty well on here, and this might be around the 1780s, might be when the Spanish first were coming into that region. I also have another little area, another spike around 1870s of the charcoal, where the possibly homesteaders came into play here. So this is kind of another, some more data to make so over 1,000 years to have one good date, it can be pretty good. We've got some reliability on some aspects of the other, when we compare it to other data, it's lining up nicely. Climate interpretations, this project combined 8 sediment-based physical and chemical analyses to infer the past climate of the Southeast Mojave Desert region. For this, we're going to limit our discussion here to grain size only. First, I'll tell you, for grain size, the changes in the contribution of coarse sediment, in this case sand, or sand-sized sediment, in lakes are often used to infer energy required to mobilize and transport material to the lake basin. So we infer the fluctuations of our coarse sediment, the sand, at Ford Lake as indicators of runoff energy. Now here's our grain sizes. We have clay to the left, silt, and sand. Oh, let me get I throw in the MCA and the LIA, the IPCC dates. And what I want to do here is, we see at Ford Lake, we've got some our flatlining doesn't happen until about here, and then it flatlines there, and then we move up into the LIA, and we've got a little bit of more flatlining, and then it starts to peak there. So we believe that at Ford Lake, our MCA and LIA fall in this line, or in this box, I should say. And remember that the whole sediment package in general was a clayey silt. So I'm going to focus on the sand. So we've got a bulk of our larger numbers going on with our clayey sand. So when we get little blips of our clay and silt, when we get little blips of our sand, it's kind of telling us something. So right here, and then clay is actually kind of has an inverse relationship with the sand. So when the sand is low, the clay is usually higher, and there's a long story to that I won't talk about at the moment. But basically, when this is low, you'll see that the clay is higher. So we've got this low area here within the dates we believe, and then it starts to increase up during the LAA. So remember, the coarser sand is the runoff energy. So we probably don't have a lot of runoff going on here. Runoff being like the water, when it precipitates, and then we've got the little ravines, the creeks, the water, the mountains all pushing water into the lake and pushing sediment. And when it's heavier, stronger water flow, we end up with larger grain sediments. And here, we don't get much, but when we do, it's telling us something. So basically, we got this little bit of a flat line here. MCA was a drought. So now we've got pretty much kind of a drought-like condition showing up in our sand. Then during the LIA, when we've got more precipitation occurring, it was probably happening, fluctuating. So we've actually see that fluctuating and increasing. in our LA timeline. Now to prove that these, to prove these, the sediment packages are different from the LAA versus the MCA, we used our timeline here. We ran these through a t-test right within that box for that. We ran it on our total organic matter, our total carbonate, and then our sediment package. And a t-test basically shows that these two periods are in fact statistically different. Excuse me. And then we have down here, when the values right here for the probability, the t probability, are less than 0.05, they have a 95% chance, or there is a 95% confidence that these climatic time periods are not similar to one another. So there is a difference between the MCA, or the LAA, and the MCA. And you can see these numbers compared to these are different. So we're seeing that statistically now, the sediment from the total carbon and total organic matter do show a difference between each other statistically. We also ran an F-test that demonstrates their variance is also statistically different. So climate forcings in the Ford Lake region, we have winter hydroclimate in the coastal southwest United States, which is strongly linked to Pacific Ocean atmospheric dynamics. So another way to think of ENSO and PDO is to consider them as drivers or forcings to the study region's winter hydroclimate. So basically our winter precipitation. As a result, we compare the Ford Lake interpretation to several published indices of ENSO, PDO, and other ocean-related data, such as sea surface temperatures. These records include tropical Pacific Ocean sea surface temperatures, Santa Barbara Basin sea surface temperatures, and PDO reconstruction. And that is the data from that with our Ford Lake, Ford Lake, sand and clay. So we've got sea surface temperatures all here and our PDO here. Down here we've got when the lines for these guys, for the two sea surface temperatures, are more to the right on their graph, then that's El Nino conditions, warmer sea waters. So this is our sea surface temperatures. So when we got warmer action going on, this is actually a gradient, so it'd be kind of a reverse deal. I'm throwing in the MCA and the LAA with for the IPCC and ours, where we think it's happening for our data. And it all is starting to line up. So over here we've got it trending downward, so we've got a La Nina, which is drought. Up here we've got the fluctuations again, which seems to be the pattern going on for the Little Ice Age, but it's generally increasing in trend, and that follows our clay and sand at Ford Lake. Also, we use the Lake Elsinore, Zaca Lake, Silver Lake, and Abbott Lake. They all show a strong connection to these Pacific forcings, and so PDO and sea surface temperature data comparisons. So basically, Ford Lake provides another piece to the paleo puzzle, showing that coastal interior Mojave winter climates were near similar during the MCA and LA. So, the Ford Lake sediment record represents the first Mojave-only paleohydrological reconstruction spanning the medieval climate anomaly, Little Ice Age, to the present. One, our hypothesis that Ford Lake would reveal a hydrological change from dry MCA to a wet LAA has been verified using the relative percent sand values during each period. Two, our research divulged the dominant forcings driving the hydrologic variability at Ford Lake is indeed the Pacific sea surface temperature, and the PDO. I'd like to thank my family and friends for supporting me through this. People that helped me with the go out to the field and work on that. There's some of the work I references, and that's that.